in this problem, we have to find the change in properties of a gas, carbon dioxide. In this case, we have to find change in enthalpy, change in entropy, and the initial state and the final states are given to us. We have to use PG and the IG models and verify the answers using suitable test calcs. Okay, let's begin with the PG model first. We know delta H is given by Cp times delta T. And entropy change is given by Cp ln T2 over T1. And this is the simplified version of the gas model where Cp and Cv are assumed constant. As a result, these simple formulas results. So let's pick up the properties. And before that, let's list what is known about the states. State 1, pressure is known, and temperature is known. And for state 2, the pressure is increased by tenfold, and temperature also has increased quite a bit. To pick up the material properties of a gas, using the perfect gas model, we log into test. In the property tables module, find the PG model row, and table C1 contains the list of properties, and the properties that we'll need for carbon dioxide right here are Cp values. Enthalpy depends on Cp, and of course we'll need probably the R value because entropy, for entropy calculation, we'll need that. So let's write those down and write those down. So now that we know Cp, and R, well, I'm approximating the values a little bit here, and that gives us immediately what is enthalpy for the PG model is Cp delta T, Cp T2 minus T1, and if we substitute, you can show that it turns out to be 761.4 kilojoule per kg. The entropy change turns out to be, let's plug in the number, Cp 0.846 ln T2 over T1 minus R 0.189 ln P2 over P1, and this can be calculated to be okay. So these are our PG model manual solutions. Okay, let us now verify the solution. For that, we go back to property tables module, and we can find the test calc right next to the PG model. In this row, the first one explain what PG model is about, the animations explain a little more, and the test calc is right here. If we click, you have to use Firefox, and as you can see, the test calc is launched right under this PG model row. We'll center it, select carbon dioxide. Now if we don't select the gas first, you cannot enter any properties. So state 1 is already the default state. We know the values of pressure and temperature. We can just hit enter or click the calculate button. State 1 is found, For state 2 again, we click the checkbox, enter the pressure. The unit is already kilopascals and 1200 Kelvin. Notice that we could select any unit from here, available, a lot of available units. So you can mix and match the units in a given problem. Click the calculate. So state 1 and 2 are selected. We could pick up the values of enthalpy. Look, it's a negative value. It may not match with any value in any other tables, but what matters is the difference in enthalpy in most problem. So we can just calculate the difference in the IO panel, H2 minus H1. And this is and S2 minus S1 will be just as easy to calculate. And as you can see, the values of 760 we got manually, 761, which is quite close to the value of entropy difference. Also, we got 0.7376. So we'll say that our solution has been verified. Okay, now let's get back to the IG model. So we'll just write down that they have been verified. By the way, before we do so, one thing to note, after doing the calculations, we can go and pick up, take a look at how they look in a TS diagram. This becomes very valuable in advanced calculations. So you can see the state 1 and 2 has been found. Entropy has increased as temperature increases. If you click on P equals constant line here, those constant properties lines are right on top of this diagram. And you can see the constant pressure line has been drawn. So this must be the 100 kPa line. And this is the other one is the 1000 kPa line. Anyways, we will continue with our evaluation of properties. Just one more thing. Just suppose the question is changed. Suppose we are now interested to find the same property differences. Instead of carbon dioxide, let's say we want to find it for air. All we need to do is to select air and click the super calculate button. As a result, all the states are recomputed, and now we can find our new values, H2 minus H1 and S2 minus S1. So for air, the same corresponding values are 903 and 0.73 approximately. So let's write those down for air also. So we can write down delta H PG for air is 903 and delta S for using the PG model for air is 0.73 kilojoule per kg. All right, now let's evaluate these properties for carbon dioxide first using the IG model. We know for IG model, enthalpy difference is integral Cp dt. Cp is now not a constant, so it's H at T2 minus H at T1, where enthalpy can be directly found from the tables. So if we go back to, let's go to the first one, property tables. This time let's select the IG model. This is the row. Let's find carbon dioxide, which is right here. Now as I click carbon dioxide, the tables of carbon dioxide is displayed here. Notice that carbon dioxide, this time the values have a bar on top, that is, these units are per kilomole. So to get back per kg, these values we have to divide by 44, the molar mass of CO2. Okay, so let's find out the values for enthalpy. This is 300 Kelvin and this is 1200 Kelvin is down there. So we can pick up the values of enthalpies and divide them by, see, one is here. This is one value, and we saw the other value already. Sorry, did I do the wrong? 1200 Kelvin is 53,848. Okay, so let's go back. So delta H turns out to be HT2, which is minus 9431 by 44, which turns out to be 1009. So for the IG model, the CO2 enthalpy change seems much higher than what we got for from the PG model. These results are also for CO2. Obviously, CP variation cannot be easily neglected away for carbon dioxide. Okay, let's calculate entropy change also, and recall for an IG model that entropy at a given pressure and temperature has one component which depends on temperature alone, another component that depends on the pressure divided by the standard atmospheric pressure. So therefore, if we use this, what happens for delta S for the IG model is that S0 T2 minus S0 T1. This is the temperature dependence of entropy, and this is the pressure dependence on entropy. And this can be picked up from table, ideal gas table. So if I continue, I can write that as delta S IG for CO2. Again, we need to find S at T2, S0 at T2, S0 at T1, and we already know R and P2 and P1. So let's go find these values. The values are again listed in the same table. S0 is right here. So from this table, the 300 Kelvin value is right here. Of course, we have to divide by 44. So keeping that in mind, we substitute these values, getting 308 for this. .189 thousand by 100 kPa, and that turns out to be approximately 0.847 kilojoule per kg Kelvin. Okay, so let us notice that the value of entropy change is not as bad as in the PG model. But now let's verify our IG model calculation. To do so, here we have our PG model results. Let's okay, let's go launch. So to close this test calc, we can click here again and come to IG model. Launch the IG model test calc right here. And by the way, if you click on the animations here, again you can, what we just now covered, how the enthalpy of an ideal gas varies with temperature is shown here, and how the entropy change is shown here. So let's go launch the, instead of the animation, let's the ideal gas model test calcs. Just click on that cell and the test calc will get started. We begin by selecting CO2. The interface is just the same, whether it's IG model or PG model, except CP, R, etc. are now Cp is not a constant, it's a variable. It depends on temperature. Look at the value of Cp, and as we change the temperature, you'll notice 1000 kPa, 1200 Kelvin. You'll see that Cp has increased 1.227. Go back to state 1, 0.84, quite a bit. So we can come back and verify. The verification answer will be on the IO panel, H2 minus H1 and S2 minus S1. It should be, and the answers obviously matches what we did, so we did correctly. One thing must be emphasized: the absolute values of enthalpy between different tables in different books may not match, but the enthalpy difference must match, and it is the enthalpy difference that is that appears in any solution. The reason is that what enthalpy is zero is very difficult to define. There are different standards in different countries, different so basically what you call zero enthalpy will make your table numbers different between different tables. However, once you pick your reference enthalpy, all the enthalpy at different temperatures will automatically vary the same way. Therefore, the difference will not be would be the same. Doesn't matter what table or what calculator you use. Now let's repeat this calculation for air now, like we did before. Again, click Super Calculate, and it's relatively easy. So H2 minus H1 would be for air, and here is S2 minus S1 for, oops, I thought H2 minus H1 and S2 minus S1. So notice we found the enthalpy difference to be 978 and 0.818 or 819. So if you go back and write them down, so therefore delta S or delta H using the IG model for air is 978, and delta S for the IG model for air is 0.819. The reason I'm doing this is it's very easy to calculate, but also it's better to appreciate. Look, 978 versus, I thought we did that for PG model 903. Notice the difference between the PG model and IG model. This is the PG model value, is not that big, and especially entropy 0.73, 0.82, whereas for CO2 it's much bigger. And for gases such as argon, helium, which are truly perfect gases, there'll be absolutely no difference. So this is just to show you that using the property tables, you can not only learn about a particular model, and by model what we mean is that a set of assumptions that groups a bunch of working fluids together, like solid liquid model. PC model means all the phase change fluids, and PG and IG model are simplified gas models. Actually, PG model is the further simplified than IG model. And then you can see that we can use the tables, we can use the animation, we can use the TESTcalcs, and we can even have a little bit of background about a particular model. If you click on that cell, it'll bring up a PDF file reminding you about how properties are calculated. So this is, in a nutshell, a lot of information organized for convenient problem solving.